In the final years of the conflict, the Third Reich shifted its efforts away from the front. In hidden tunnels, underground facilities, and forested areas, groups of engineers and technicians began developing weapons unlike anything seen before. The objective was no longer to improve troops or vehicles, but to create tools capable of immediately destroying the enemy. Many of the plans remained on paper due to their size, cost, or technical unfeasibility. Some were tested, but did not offer decisive results. The documents recovered at the end of the war showed the extent to which they tried to manufacture devices capable of causing massive damage without warning. What were the secrets of those weapons that wanted to annihilate millions but failed in the attempt? Silbervogel, the aircraft that planned to bomb from orbit. The Silbervogel project emerged as a German attempt to develop a space bomber during the Second World War. Its design proposed the use of a booster ramp that would allow it to reach hypersonic speeds, with the aim of launching bombs on distant targets. The vehicle was conceived to take off with the aid of an inclined rail and an additional rocket system that would provide the initial thrust. After leaving the ramp, the apparatus was supposed to continue ascending up to 150 kilometers of altitude, with an initial acceleration of up to 20 times the gravity. In that trajectory, it would enter a partial orbit that would allow it to glide long distances, skimming the Earth's atmosphere. The original design specified a trajectory with successive bounces over the upper layers of the air, which prolonged its potential range without the need for continuous propulsion. The body of the craft had a length close to 28 meters and a wingspan of 15 meters. Its total weight at launch would reach 100 tons, while empty, it would weigh about 9. The initial thrust of the main engine would be 610 tons for 11 seconds. The dimensions and characteristics of the engine were intended to take the vehicle to an approximate speed of Mach 10. The Silbervogel vehicle was designed with a very demanding aerodynamic and thermal load. Upon reaching suborbital altitudes and extreme speeds, the skin of the apparatus would be subjected to temperatures exceeding 1,300 degrees Kelvin. To withstand these conditions, the design foresaw the use of materials capable of resisting high temperatures without compromising the structure. The blueprints proposed that the apparatus would release its explosive payload over the target after a trajectory correction phase, called the third direction phase, just before the release point. Then, the vehicle would follow its descending trajectory and land on a pre-established runway after having traveled thousands of kilometers. The main engine, classified as a 10, had a loaded mass of almost 70 tons, while its empty structure weighed just under 17. Its height was 20 meters, and its diameter was slightly more than 4. This engine offered a thrust exceeding 2 million newtons, with a specific impulse of 247 seconds, reduced to 210 at sea level. The estimated duration of combustion was 55 seconds. The upper module, designated A9, had a total mass of more than 16 tons and a structural mass of 3. It measured slightly over 14 meters high, with a diameter of 1.5 meters and a wingspan of slightly more than 3 meters. Its thrust was almost 300 kilonewtons, with a combustion duration of 115 seconds. Its maximum altitude would reach 200 kilometers, and its flight range would be 1,000 kilometers. In one of the design schemes, the apparatus was projected to ascend rapidly to 3 kilometers at Mach 1.5 speed, and then continue climbing for about 8 minutes, until reaching its suborbital ceiling. From that position, it would perform an intercontinental flight with atmospheric skipping before releasing its payload. One of the documents that mentions this project is a research study by the German Luftfahrtforschung, where a rocket propulsion system for long-range bombers is analyzed. The report details the vehicle's architecture, its navigation system, and the re-entry parameters. The planned guidance system included instruments capable of maintaining the orbital trajectory without significant deviations and relied on mechanical and gyroscopic mechanisms. Aerodynamic control was achieved thanks to movable surfaces installed at the rear of the apparatus, which allowed for precise course adjustment during the phases when it flew within the atmosphere. When comparing the Silbervogel to space vehicles developed later, such as the American Space Shuttle, it was clear that it had an advantage. Its lift-to-drag ratio reached a value of 5, while the North American model barely reached 4.5. This difference reflected greater efficiency and prolonged gliding. After the war, the knowledge accumulated in this project sparked the interest of several powers. Attempts were made to recruit the design leaders, including Eugen Sänger and his collaborator Irene Sänger-Brett. The technical documents on the Silbervogel were studied in detail by both the United States and the Soviet Union, who sought to leverage the German experience in advanced space technologies. In a later stage, Sanger developed theories on photonic propulsion as an evolution of the initial Silbervogel concepts. These ideas considered the use of light-based reaction energy, capable of achieving relativistic speeds with very small masses. Although these proposals were not directly connected to the Silbervogel, they shared the objective of creating transport systems that would surpass the known atmospheric limits. The final design phase included estimations of the thermal effects of the flight, the power generation during the initial impulse, and the vehicle's capacity to withstand the stress of multiple atmospheric skips. In particular, it was calculated that the external surface would experience extremely high dynamic pressure during re-entry. The Silbervogel was never built, but the associated studies marked a technical precedent that would influence the subsequent development of missiles, orbital vehicles, and advanced propulsion theories. The concept of suborbital flight combined with atmospheric skipping was revisited decades later in American and Soviet aerospace proposals, albeit with very different technologies. Sonnengewehr, the space mirror that targeted Earth. The regime chose Hillersleben, a locality surrounded by hills and dense vegetation, to erect its main weapons testing site. There, a group of more than 150 specialists in physics and engineering tested dozens of prototypes, several of which were used during the clashes. When the Allies took control of Germany in May of '45, the complex was left behind. In the abandoned facilities, they discovered weaponry in different phases of preparation. There were rocket launchers, armored vehicles adapted to fire at long range, 600mm cannons, and many other pieces that were about to be implemented. Among all the documents found, a design attributed to Hermann Oberth stood out, who would later be considered a key figure in the development of space technology. The project, known as Sonnengewehr or solar weapon, proposed a structure located in near-Earth space. According to the papers found, the station would be assembled in parts built on the surface and then transported off the planet. The procedure was similar to the one that would be used decades later for the International Space Station. There was even a description of how to generate artificial gravitational force from a constant rotational movement. Among Oberth's proposals, the one that most attracted the regime's high command was the creation of a concave reflector with an approximate diameter of 3,000 meters, capable of redirecting concentrated sunlight toward a specific point on Earth. It was an idea that vaguely recalled a principle attributed to Archimedes, where rays were used to burn rival ships centuries ago. The German technicians, based on Oberth's calculations, concluded that the ideal location for the mirror would be about 8,200 kilometers in altitude. The compound chosen for the reflective surface would be metallic sodium, a material that effectively reflects light and is common in the natural environment. Although sodium reacts violently upon contact with water, this detail did not generate inconvenience, as there is no moisture in the vacuum of space to alter its properties. The different sections of the mirror would be placed into orbit using an evolution of the V-2 missile. This new version, named V-11, was designed by Werner von Braun. The artifact would have the capacity to send people off the planet and, at the same time, would be used as an intercontinental attack vector, with the possibility of impacting North American soil, just as the V-2 had done over British territory. The devised system also included internal spaces intended to house the crew members. Some parts of the project may seem naive from a current perspective, but in that period, knowledge about space conditions was minimal. The electrical supply would be generated by means of devices similar to dynamos, which would function thanks to solar radiation. Operators would wear shoes with magnets to walk on the interior surfaces without floating, and breathable air would be obtained through crops. A controlled pumpkin plantation would absorb the carbon dioxide released by the crew and continuously release oxygen. The orders would be sent from the ground base using coded signals. Once received, the team in orbit would use a control system to orient the mirror toward a point on the planet. There was no risk of direct attack against the structure, since at that time no force had the means to destroy it from the ground. With the entry of the Allied forces into German territory, all preparations were abandoned. It is probable that, even if it had been built, the projected light